Hi there, welcome. In this class we consider mixture models, which are a different type of models with respect to the models we have seen so far. In this class, the most important model that you probably know is Credit Risk Plus by Credit Suisse. Now, in mixture models, we have that the different counterparties, the probabilities of default of the different counterparties are jointly dependent on a set of common factors. These common factors can be macroeconomic factors, can be sector-specific factors, or every combination. And the idea is that these are the only components that build the dependence among the different counterparties. From a probabilistic point of view, we assume that once we know what are the common factors, then the defaults of the different counterparties are conditionally independent. As you can see in the picture here below, we have two counterparties, A and B. They depend on some common factors. Obviously, they also have their own idiosyncratic factors. And if we can isolate the common factors, the two counterparties can be considered as independent. So their probabilities of default will be conditionally independent. Now, what is the interest in mixture models? If you remember what we have said so far about the multivariate extension of credit metrics, also in that case we had some common factors. And actually, this is the link to tell you something about the relationship between mixture models and threshold models. In particular, every threshold model may have a mixture model representation. And later on in the course, we will see that this is quite useful because mixture models are more efficient from a computational and statistical point of view. It's easier to estimate the parameters.
Let psi be a p-dimensional random factor vector. It contains different factors building the dependence among our counterparties. The random vector y is said to follow a Bernoulli mixture model with factor vector psi if, conditionally on psi, defaults are independent Bernoulli random variables. This tells us that conditionally on a realization of psi, the joint distribution of defaults is just a product of Bernoullis. In order to obtain the unconditional distribution of the vector y, we need to integrate over the distribution of the vector psi, which plays the role of a mixing distribution. The marginal probability of default of each counterparty I can be obtained by computing the expected value of pi over psi.
In order to simplify the exposition, let's consider one-factor models. In one-factor models, essentially we assume that we only have one common factor. We are not specifying what this factor accounts for, but conditionally on this common factor, all the counterparties are independent, and so are their probabilities of default. As you can see in the slides, the notation simplifies, but from a theoretical point of view, there is no major difference. It's just because it's easier to grasp some of the details.
Let's assume that all the probabilities of default are the same for all counterparties. In this case, the Bernoulli mixture model is called exchangeable, since the random vector y is exchangeable. In other words, the joint distribution of y is immune to permutations of the elements in y. Let Q be the probability of default of whatever counterparty, say the first one. Because we are assuming that all the PDs are the same, the counterparty we choose does not really matter. Set G of Q to be the distribution function of this mixing variable. For the Bayesian among us, the G of Q plays the role of the Definetti measure. The defaults are IID conditionally on G of Q.
The assumption of exchangeability may seem a strong assumption, and actually it's better to drop it, but if you want, it's like we are considering an homogeneous group of companies. Say we are just consider obligors with a triple B rating. Within this class, we can really assume that the different counterparties are exchangeable. So the order in which I observe them is not really relevant for the computation of the joint probability of default.
Conditionally on a realization of Q, the number of defaults capital M is the sum of M independent Bernoullis with parameter Q. This tells us that capital M is a binomial QM. The unconditional distribution of capital M is obtained by integrating over Q. The formula tells us that the probability of observing K defaults is a combination of a binomial mixed by the mixing distribution G of Q, which determines the behavior of Q. Let pi be the probability of default of each obligor. We can easily show that this probability corresponds to the expected value of Q. With pi k, we indicate the joint probability of K defaults. In this case, we see that this probability corresponds to the kth moment of Q. The probability of default of one counterparty is always the same. Hence, the unconditional default probabilities of first and higher order correspond to the moments of the mixing distribution. The computation of the covariance, thanks to the conditional independence hypothesis, tells us that all the joint behavior is given by the mixing variable Q. In fact, the covariance between yi and yj is just the variance of Q, which is by definition non-negative. This tells us that in an exchangeable Bernoulli mixture model, also the correlation is always non-negative.
So what are the economic implications of this? Since correlation is always non-negative, this model supports the idea of contagion. That is to say, the idea that one default can really trigger an avalanche effect in our homogeneous group of counterparties. It is a model that takes into account, that actually fosters procyclicality. That is to say, the possibility that during a bad period, during a crisis, there is this avalanche effect and this self-reinforcing behavior in the number of defaults over time. It is also a model that, despite its simplicity and, if you want, its theoretical framework, is able to generate very different cases, and we just simply need a few assumptions. Consider the mixing distribution G of Q. If we assume it to be a Bernoulli distribution with 50% probability on 0 and 50% probability on 1, then we can show that the correlation between yi and yj, that is to say the indicators of two defaults in our portfolio, is 1. And 1 means perfect linear dependence, positive dependence, or in more risk-theoretic words, perfect comonotonicity.
Let's now assume that the mixing distribution is a beta. We know the density of a beta. We saw it when dealing with recovery rates. Since we know that the probability of default of k counterparties corresponds to the kth moment of Q, we just compute the kth moment of a beta. Here it is on your screen. As for the number of defaults, we can use the mixed binomial, obtaining the famous beta binomial distribution. Let's consider an example, a theoretical one for the moment. Imagine we observe defaults over n periods of time for a homogeneous group of companies. For every t, let mt represent the number of observed companies at the beginning of period t, and let capital MT be the number of defaults in the same period. If defaults follow an exchangeable Bernoulli mixture with beta mixing, we know that capital MT is conditionally binomial, and the number of defaults in any period is a beta binomial of parameters A plus capital MT and B plus MT minus capital MT. Writing the likelihood is simple, and the estimation of the parameters can be easily performed with MLE.
There are situations in which the beta mixing model is not at all a bad model, a model that despite its simplicity you can actually use with some good results. In my research, I have developed more advanced versions of this construction, and in week 5 I will share with you some insight about the use of this model in practice. For the moment, I thank you for your attention. See you next time, and goodbye.